This is the second part of the lecture on concrete. We have looked up to now, we have, well, this is the second part, of the lecture on concrete. Until now we have looked at examples of applications of concrete in structures and other projects. Now we are going to look at the components that make up concrete, what are their functions within this material, and later on we will look at the properties. On this header slide we have a picture of the Petronas Towers in Kuala Lumpur, Malaysia. It is a structure with 88 floors. For a long time it was the tallest building in the world. It is made out of reinforced concrete, the framework is reinforced concrete, and on the facade we have steel and glass. So from the outside it does not look like a concrete building, but it is very much reinforced concrete structure. This is a good example of how concrete can reach heights, and this went on to become the way of making very tall structures, skyscrapers with a concrete frame and with steel and glass on the facade. Now what is concrete made up of? Basically concrete is made up of cement, basically of cement, and when cement reacts with water it forms a hard material. We will see later on what are the reactions which lead to this later on we will see what are the reactions which lead to this hardening and solidification. The majority of concrete consists of aggregates, which are pieces of stone. They are classified as fine aggregates and coarse aggregates. Fine aggregates are material that are smaller than 5 millimeters in general, and those that are more than 5 millimeters are called coarse aggregates. And basically we have pieces of aggregates of different sizes within the concrete, and we have different fractions of aggregates such that the smaller aggregates fill up the space between the large aggregates, so that the voids are reduced, and within the extra space that is there the cement paste fills up and acts as the binder between these aggregates. So basically concrete is made up of stone pieces or aggregate pieces, and they are bonded together and the voids are filled up with cement paste, which hydrates, becomes hard, and gives us a solid material. We also have other materials that can be added to concrete, chemical admixtures. We will see them in the next lecture. These give special properties, make it easier for us to mix concrete better and to get long term behavior that we would like to. There are mineral admixtures which supplement the function of the cement, which help us save cement in some cases, and fibers could also be added to make the concrete more resistant to cracking. What is cement? Cement is a hydraulic material, that is, it is capable of setting, hardening, and remaining stable under water. Portland cement is a hydraulic material. It is composed mainly of calcium silicates, and this is obtained by generally heating a mixture of limestone and clay in a kiln at about 1400 to 1600 degrees Celsius. Limestone is used because it is a common source of calcium oxide or lime. We also need silica, and therefore iron bearing aluminosilicates are used to provide a source of silica. In some cases we find that in India the limestone itself has a very high content of silica, and there clay is not necessarily added, but in other cases where the limestone is purer and does not have much silica, has impurities, clay is added, and this is because clay in its finely divided state can mix well and can be processed easier. The aluminum and iron oxides that are present also act as fluxing agents. Fluxing agents decrease the fusion temperature and therefore, the cement can be produced at lower temperatures. When we look at the cement composition, we have different components, and in these tables we will see the different compounds that are present in cement and also what is the cement chemistry notation. What you see in the second column is the cement chemistry notation used to denote the different compounds, and this is useful to remember because later on we will not use the exact chemical formula, but base our equations on these notations. Cement has a very high percentage of calcium oxide, it is about 60 to 70%. Then we have silica 17 to 25%, and then we have alumina, iron oxide, magnesium oxide, other alkalis like potassium oxide, sodium oxide, and some amount of sulfur trioxide. And as I mentioned, here you have the cement notations. Calcium oxide is denoted as C, silica as S, hydrogen as H, water as H, alumina is A, iron oxide as F, magnesium oxide as M, potassium oxide and sodium oxide as K and N respectively, sulfur trioxide as S bar and carbon dioxide as C bar. You find that most of the components, you find that the majority of the components are calcium oxide and silica, but we also have some other compounds which play some important roles in different aspects. For example, alumina gives us, later on we will see, early setting behavior when ettringite and monosulfoaluminate are formed, and the alkalis which are present, potassium and sodium oxides, can affect the alkali aggregate reactivity, alkyl carbonate reactivity, and also to some extent how superplasticizers are effective in concrete. So, even the minor compounds have some roles to play in the hydration and behavior of the cement concrete. Now, these compounds are present as in complex forms. The main components which react with water and decide the behavior of hydrated cement and consequently those of concrete are C3S, which is tricalcium silicate, also called alite. 45 to 60% of cement is made up of C3S. Then we have dicalcium silicate, also called belite, which is denoted as C2S, typically having a percentage weight of 15 to 30%. Then we have the minor compounds, tricalcium aluminate. This is what gives us ettringite and monosulfoaluminate, decides how concrete sets very early. Then we have tetracalcium aluminoferrite 6 to 8%, this is denoted as C4AF. Then we have gypsum, which is added to cement so that the setting is not too fast. So, gypsum is added during the processing of cement so that there is not quick setting of cement in the concrete, and this is needed because we need time to mix and to place the concrete. About 3 to 4% of gypsum is added to the concrete, and this is the notation of gypsum in terms of cement chemistry. Now, what happens when cement is mixed with water? The primary compound of interest is calcium silicate hydrate. This is the glue that bonds the aggregates together, that gives form to the concrete and gives concrete its strength. There are two compounds which give us calcium silicate hydrate. First to react will be the C3S, and here you see the reaction. C3S with water gives us the calcium silicate hydrate and calcium hydroxide along with the emission of heat. This is a moderate rate reaction. It gives very high strength early on and there is a lot of heat liberation. The other compound which also reacts with water is C2S. Reacting with water gives us the calcium silicate hydrate and calcium hydroxide along with some heat. This is a slower reaction. Initially it does not impart a lot of strength, but later on it gives high amount of strength. There is lower heat liberation in this reaction than in the former. We notice a couple of differences between these two reactions. First of all, when C3S reacts, there is more heat produced than when C2S reacts, and also we find that when C3S reacts with water, we have more calcium hydroxide produced in this reaction than when C2S reacts. So, these two differences have important consequences. There is a tendency nowadays to have cements with higher C3S content, so that we get earlier strength gain. This means that we are producing more heat, which can lead to cracking if not cured properly and taken into account in the early stages. Secondly, we have higher amount of calcium hydroxide produced in the first reaction, and calcium hydroxide is sort of a weak link in the hydrated cement paste. It does not offer bonding behavior, and in terms of durability it reacts more easily with other compounds and gives rise to durability issues. So, we have to be very cautious when we go towards cements with very high C3S contents, and it may not be necessary and advisable in most applications. In general, we see that calcium silicates C3S and C2S react with water to give us the calcium silicate hydrate, or this is also called the CSH gel. This is what gives us the binding properties of hydrated cement paste, which holds the aggregates together and gives a compact impermeable structure to concrete. Along with that, we have calcium hydroxide. This is not something that provides a lot of strength and can also affect the durability of concrete. Other than these two reactions, we also have the formation of ettringite and monosulfoaluminate, where we have C3A reacting with the gypsum and water to give us ettringite, and this occurs with a lot of heat evolution. This occurs very early on. It is a fast reaction, does not contribute much to strength, but it gives off a lot of heat, which again can affect the early cracking of concrete due to very high thermal stresses. When all the gypsum is exhausted, ettringite reacts with the C3A that is present, further C3A that is present, to give us monosulfoaluminate, and this is the overall reaction. We have tricalcium aluminate reacting with the gypsum to give us monosulfoaluminate with a lot of heat evolution. C4AF also reacts with the calcium hydroxide to give tetracalcium aluminate hydrate and ferric aluminum hydroxide. C4AF can also react with gypsum as in the case of C3A, but it is much less reactive than C3A. So, these are the different reactions which occur when cement is mixed with water, and these are called the hydration reactions, and we have also seen what are the products that form as these reactions occur. Now, these reactions occur over a period of time. They do not always occur at the same time, and each of them has a different rate of reactions. Initially, as soon as we mix cement and water, in few minutes we have the ettringite formation occurring. This is this curve, you see that ettringite has started to occur along with some calcium hydroxide. In a few hours we have setting occurring, we have the ettringite almost completing its hydration. Later on the ettringite changes into monosulfate. Now the CSH starts to form as setting occurs, the network of CSH takes form and gives rise to the hardened cement paste. This hardening and CSH formation occurs over a long period of time. In normal concretes it takes at least 28 days, that is why we have 28 days as the reference for checking concrete strength and other properties, and could continue even further. As these reactions occur, the porosity of the hydrated cement paste decreases. Initially the porosity is caused by the presence of water. As the water is consumed by the hydration reactions, a network forms in the cement paste, the porosity drops and it becomes very low once all the hydration has occurred. That is shown figuratively at the bottom. Initially we have the cement particles in water, the cement starts to hydrate, we have initially ettringite forming, those are the needles that we see here. The ettringite starts to form very early, in few minutes to hours. Then we have a network structure forming due to the hydration of the C3S and C2S. Finally we have a hardened cement paste with a network of the cement hydration products, and we have a compact hard structure, and the pores that have been created by the water are filled up as the hydration products form. We also saw in the reactions that all of them were exothermic, there was heat evolved, and if we look at the rate of heat evolution over time, we have a graph such as this, where we have an initial stage that occurs very early as soon as the cement and water are mixed, or when concrete is mixed with water, there is a first peak that occurs due to the primary formation of ettringite. Then afterwards there is a dormant period, there is no significant heat evolution here, and this is the part that we use for mixing and transporting concrete. Setting has not really completed, the concrete is still in a fluid state and we do not have hydration occurring to a great extent. After that we have stages 3 and 4, where we have the C3S hydration peak and the C3A hydration peak occurring, and then afterwards we have an equilibrium stage where the temperature reaches that of the environment, that is stage 5. So in stage 1, which lasts very little time, usually during the mixing process, where we have this first peak coming from the ettringite formation, then we have a dormant period which lasts until the initial setting, occurs in about 2 to 4 hours, and this is the period where we should finish the transportation and the placing of concrete, so that when the network of hydration products is forming, there is no disturbance to the concrete itself. In stage 3 we have the rapid reaction of C3S, the peak reaches at about 8 to 10 hours after the final set, which occurs at 4 to 8 hours, that is the concrete has completely set, it has become a solid mass instead of semi solid mass, and hardening starts. In stage 4 the rate of reaction now slows down and we reach the steady state where there is no further increase in temperature, or rather there will be a decrease in temperature which occurs after a day or so, and finally we have the steady state where temperature is reaching an equilibrium with the external temperature. During hydration, we saw that lot of hydration products are formed. How do these products look like? This is a micrograph from Young et al. Showing a 7-day-old hardened cement paste, and we see the different hydration products here. In the bottom left, this is a cement particle coated with calcium silicate hydrate. This spongy mass is the calcium silicate hydrate, and the needle like structure that we see is ettringite. This ettringite later becomes monosulfoaluminate. You have these flakes here, which is calcium monosulfoaluminate, and this crystalline structure that we see is calcium hydroxide. This crystal that is here is calcium hydroxide. If we take a closer look at calcium silicate hydrate or the CSH gel, these are pictures from Mehta and Monteiro, we see that we have a spongy structure made out of these flakes or plates of calcium silicate hydrate. These have a nanometric scale, these form this spongy appearance of the CSH. The CSH has a calcium oxide silica ratio of 1.5 to 2, very high surface area because of this flaky nature, about 100 to 700 meter square per gram. These are covalent ionic solids bonded together with van der Waals forces, and this makes up about 50 to 65% of the structure of the hydrated cement paste. We also see here, and we will continue to see when we look at the micrographs, is there is a lot of space between the particles, and this is the capillary space, which is initially filled with water and later on could remain as capillary porosities. In the main hydration reactions, we saw that calcium hydroxide is also produced. This is known as Portlandite in the context of cement chemistry. These are large hexagonal crystals like the ones that you see here in these pictures. They have low surface area, they are quite compact and very low van der Waals forces. These do not bond well with anything else. So, even though the calcium hydroxide itself is quite strong, it does not impart any strength to the hydrated cement paste or concrete, because it does not bond well with anything else. It does not bond the aggregates together or keep the hydrated cement paste together in a strong manner. So, that is why we find that calcium hydroxide is a weak link in the hydrated cement paste, and further this reacts with other materials to lead to durability issues. The volume of calcium hydroxide is about 20 to 25% in the hydrated cement paste. Other than these two structures, we have small quantities of ettringite and monosulfoaluminate. Ettringite, which forms first, is this needle like structure that later becomes platelets of hexagonal crystals, which is the monosulfoaluminate. Together they take up about 15 to 25% of the hydrated cement paste. We said that there is a lot of porosity in the hydrated cement paste, and here in this nice graph by Mehta and Monteiro, we can see how the microstructure is distributed in the cement paste. In the very low end, in the nanometric scale, we have the sheets or plates of calcium silicate hydrate, and within these sheets there is some amount of gaps, the gel porosity in the nanometric scale. Then in the 10 to 1000 nanometer scale, we have the capillary voids. These are the voids or the spaces between the CSH particles. This gives rise to capillary stresses, and later on we will see that it influences how shrinkage occurs in concrete and creep and so on. So, capillary porosity is something that we would like to decrease, and one way we will see how we do it is by using mineral admixtures to complement cement and to reduce this capillary porosity. In the micron scale, we have the hexagonal crystals of calcium hydroxide. In cement paste, we have the lumps or aggregations of calcium silicate hydrate that we saw in the pictures that I showed you. So, this basically makes up the structure of the hydrated cement paste. However, there are air bubbles and air voids which can be quite large. They can even go up to few millimeters in size, and we find that in some cases we intentionally put in air bubbles, that is, we entrain air to give durability against freezing and thawing. There are admixtures which, when added to the concrete, produce tiny microscopic bubbles, several of them not connected, distributed in the mass of the hydrated cement paste, and this gives better freeze thaw durability to concrete, because when the water becomes ice it tends to expand, and these air bubbles give space for expansion rather than the water having to expand within the capillary pores and leading to cracking due to this expansion. We also could have large air voids which have to be avoided. These air voids can be removed by compaction and they are not desirable in the concrete. So, this gives you the range of aspects or morphology that occurs within the hydrated cement paste spanning 1 nanometer up to about 10 millimeters scales. Before we go on to the other components of cement, we also have to understand that cement is a standardized product. There are standards in different countries that govern the properties of cement, and this is done to get some sort of a uniformity. I have listed here the some of the cements governed by the Indian standards, and these are the ordinary Portland cement, which can be found in 3 grades: 33, 43 and 53. This grade indicates the minimum strength to be achieved in a standard cement mortar at 28 days, and these are the respective standards that are used for the 33, 43 and 53 grade. We also have some special cements such as sulphate resisting Portland cement, where we have cement that should be used where when you have very high sulphates in water or in the soil. A cement that is becoming very common and possibly is more commonly available in some places than ordinary Portland cement is Portland pozzolana cement. This is a blended cement that has a high quantity of fly ash, about 25 to 30% of fly ash. This saves on the clinker that is used to produce cement and also gives a cement that has lesser heat and gives better durability in the long run. A similar cement is the Portland slag cement, which in India can be obtained in lot of places. Then we have white cement, which is devoid of iron and therefore we get a white color. This is used for architectural purposes, for filling, for floors, for facades, where we want a white finish or we want a colored finish, which is obtained by adding a pigment to the white cement concrete. Now, a large part of the concrete itself is occupied by aggregates. The cement paste forms only a small part by volume of concrete. 60 to 85% of the volume of concrete is occupied by aggregates or stone pieces. The remaining is basically the cement paste. The significance of using aggregates in concrete, first of all, is cost. Aggregates are cheaper than cement paste or cement, and therefore, it is better to have as much aggregates as possible in concrete. More importantly, we have dimensional stability and strength that comes from the aggregates. Dimensional stability meaning that there are no changes in volume as the concrete is hydrating as far as the aggregate is concerned. This gives rise to better dimensional stability in the concrete. Cement, as it hydrates, shrinks, and due to temperature and so on, there could be changes in the volume of the hydrated cement paste. So, if we have a very high volume of hydrated cement paste, there could be major volume changes in the concrete itself. The presence of the aggregates mitigates this and reduces the volume changes that could occur in the concrete. Secondly, in most applications the aggregate is stronger than the cement paste. Therefore, we get a stiffer and stronger concrete due to the presence of the aggregates. Lastly, aggregates give abrasion resistance. So, there is less wear and tear, whereas cement paste is more powdery and can be worn off more easily. Aggregates prevent this from occurring. Aggregates have to be packed within concrete such that the voids between them are minimum, which can be filled with a hydrated cement paste. And as we saw in the previous slide, we would like the cement paste to be as low as possible to reduce the cost and also to just act as the binder and not affect the long term behavior, dimensional stability, abrasion resistance and so on. So, there is a lot of thought that has gone behind what should be the gradation of aggregates, how should the aggregates be put together, packed together, so that we have a highly dense aggregate skeleton within the concrete and require the least amount of cement paste to be used. If we have aggregates all of the same type, that is a uniform size, you see that there is a lot of space between the aggregates. So, this would require a lot of cement paste to be added. If we have a continuous grading, this is something that we already discussed when we looked at asphalt concrete, where we have large aggregates, then smaller and smaller aggregates, we will find that the smaller aggregates fill up the space between the large aggregates, and thus subsequently the even smaller aggregates will fill up the space between these small aggregates and so on gradually. So, there is very little space at the end that has to be filled up by the cement paste, and that is enough to bond all the aggregates together and give us a dense structure. Also, we see that it is better to use the largest aggregate size possible within concrete, because a larger aggregate instead of many small aggregates means that you have less surface area and you have less voids. Imagine that this large aggregate is replaced by smaller aggregates. Even though you get something like which looks like a dense structure, we can see that the smaller aggregates will have higher surface area for the same mass. That means they will have to be wetted with more water and cement paste, and more importantly you find that instead of a large solid particle, we have many solid particles, and between them there is a lot of space which has to be filled with cement paste. So, in general for concrete we would like to use the largest aggregate size possible, so that we have the least amount of cement required and we have a solid structure through most of the concrete. The exception later on we will see is with high strength concrete. In very high strength concrete we go for smaller aggregates, basically because these aggregates are stronger, the elements of the structure itself are smaller, and We also want higher workability in very high strength concretes. But generally, as a rule, in most concretes we want the largest aggregate size possible with a continuous grading, so that we have a dense packing of aggregates giving a network of aggregates and a compact skeleton of aggregates. We make exceptions to this rule in some cases. This is gap grading, where an intermediate fraction of aggregates is removed or is missing. This is done sometimes to make concrete more pumpable. This concrete could be more pumpable than a concrete that has a dense grading, because there is less interlock, the fluidity is better, and when the concrete has to be pumped over long distances or heights, a gap grading is used where an intermediate fraction of aggregates is removed. Then we have some particular types of concrete where we want the concrete to be porous, and there we use something called a no fines concrete or a no sand concrete, where the concrete is made without any fine material, and if the hydrated cement paste is not so much that it fills up all the space, it leaves porosity. So this is a type of concrete that could be used where you want drainage to occur through the concrete, say in the case of a pavement or parking lot. Later on we will look at porous concretes, and no fines aggregate gradation is used in such porous concretes. Again, some of these aspects we have already looked at when we discussed asphalt concrete. The concept is similar. In asphalt concrete, the binder which fills up the space between the aggregates is bitumen, and here we have hydrated cement paste. In addition to the aggregates, cement and water, nowadays we use mineral admixtures incorporated in the concrete. This concept started off in the 1970s, when people found that mineral admixtures, when added to concrete, increase the compressive strength, other mechanical properties, and very importantly the durability of the concrete. The concrete could last longer when certain mineral admixtures, fine materials, were incorporated into the concrete to supplement, to complement the role of the cement in the concrete. In some cases the rheological behavior is also improved. You get more cohesive, more fluid concretes with the right type and amount of mineral admixtures. Mineral admixtures could also correct deficiencies in the packing density of the aggregates. If you remember, we just talked about the need to have a dense packing of aggregates, and sometimes the aggregates available may not have the right type of gradation, and for this mineral admixtures could be used. Generally they increase the paste content because this is added on to the cement paste, without increasing the dosage. If you want to have a higher paste content, like in self compacting concrete, we need higher paste contents, so we need a filler material, and mineral admixtures are also used in those cases. When we replace cement or we increase the paste content without adding more cement, we tend to decrease the heat of hydration compared to the case where we would have only cement as the fine material. Mineral admixtures, when incorporated in concrete, also decrease the environmental impact of concrete when we use, say, a waste material like fly ash. This leads to saving of cement, saving of clinker, which needs a lot of energy, which needs a lot of raw material, and on the other hand we use a waste product that is just going to be dumped or thrown away. So there are a lot of benefits in using mineral admixtures, and in India today most of the concrete will have some kind of mineral admixture, either coming in through the cement itself as a blended cement or being added to the concrete at the mixing plant. What are the different types of mineral admixtures that we can use? We classify them as cementitious, pozzolanic and inert. Cementitious mineral admixtures are hydraulic lime, blast furnace slag and some natural cements. The most important is the blast furnace slag, because this is a waste product. When ground it could be very useful, and we saw that in the Indian standard there is also a Portland slag cement, which is a combination of clinker based cement and slag put together to give us the Portland slag cement. Another very important group of mineral admixtures are called pozzolanic admixtures. Examples of these are microsilica or silica fume, fly ash, and they could be materials of natural origin also, like volcanic ashes, which gave the name pozzolanic, coming from the Italian village of Pozzola. And these now are not cementitious, that is, they do not react with water, but they react with the calcium hydroxide. Cementitious admixtures react with water directly. Pozzolanic admixtures react with calcium hydroxide and water to give calcium silicate hydrate. Other than that, we have inert fillers with low or negligible reactivity. They could be rock dust, limestone dust, quartz dust and so on. Bentonite and hydrated lime also have been used to some extent. The pozzolanic reaction is this: when you have a mineral admixture with a very high amount of amorphous silica, this amorphous silica reacts with calcium hydroxide and water to give a calcium silicate hydrate, very similar to that which is obtained when cement reacts with water. Frequently, along with the amorphous silica, there is also some reactive alumina, which is also present in the pozzolanic admixture. This leads to an analogous reaction, a similar reaction with the calcium hydroxide to give calcium aluminate hydrate. This is not very useful to us, and it can also lead to some expansive reaction to form ettringite. This is what is of interest to us, to have pozzolanic reaction so that the calcium hydroxide is consumed. Remember what I told you before, that the calcium hydroxide is sort of like a weak link, because it does not contribute much to the strength and it can also hurt the durability. So, the pozzolanic admixture converts the calcium hydroxide to more useful calcium silicate hydrate. The different supplementary cementitious materials or admixtures can be put in this ternary diagram, where we have admixtures with very high purity in silica, such as silica fumes up here. Then we have fly ashes. We have generally two classifications of fly ashes: class F with a higher silica content, then class C fly ash which has a higher calcium oxide content. Portland cement for comparison is down here, slag is here. So, we see that these admixtures have different compositions of different proportions of silica and alumina. We see that these admixtures have different proportions of silica, alumina and calcium oxide, and depending on these proportions, the reactivity and how they behave in concrete is different. The most important pozzolanic admixtures as far as we are concerned here are silica fume and fly ash. We see that silica fume has a much higher silica content than fly ash. We have cement here in the last column for comparison. In terms of surface area, silica fume has much higher surface area than the other two. This means that silica fume is very fine, it is much smaller in size, and therefore it can react fast and also fill up the space between the particles of cement and fly ash. The pozzolanic activity also is much higher because of the high silica content and also its fineness. it is much higher than fly ash. In terms of pozzolanic activity, where this material is mixed with lime and we see what is the strength gain, we also see that it is better than fly ash. In pozzolanic activity, we are looking at increase in strength with respect to a cement concrete. So, these are tests which indicate how active or how reactive a mineral admixture is. So, let us look at some of the properties of silica fume and fly ash concretes. Silica fume, as I mentioned in the previous slide, is a material which has a very high fineness and therefore it has a very high specific surface area. The particle sizes are generally less than 1 micron, that is very small. A cement particle would be in the range of 10 microns. So, this is about 1 order smaller than a cement particle, and because it is very fine, we find that the density as produced is quite low. It ranges from 130 to 430 kilograms per meter cube. Since it is a fine material, we find that the bulk density of silica fume is quite low. As produced, it can be as low as 130 to 430 kilograms per meter cube. Therefore, sometimes it is made into a slurry with water, say 50% as produced silica fume and 50% water. This facilitates pumping and the ability to transport more silica fume. However, we also are transporting a lot of water in this process. So, this is popular only when short distances have to be covered during transportation. Another way of transporting or using silica fume is in the densified form, where lumps of particles are made out of the silica fume, and these lumps get dispersed during the mixing of the concrete. The specific gravity of silica fume is 2.2 and the BET surface area is 13,000 to 30,000 meters squared per kilogram. So, again all these factors indicate that silica fume is a very fine material, very small material, and therefore it reacts fast and can fill up the space between the cement particles. So, what are the consequences of silica fume? In the fresh concrete, we find that silica fume concrete is more cohesive, that is, it is more sticky. Since the fineness of silica fume is higher than cement, we have to have more water, but this obviously will hurt in terms of strength and durability. Therefore, to compensate this additional water demand of the silica fume, we use a super plasticizer. We will talk about super plasticizers in the next part of this lecture, but super plasticizer are chemicals which facilitate the workability, increase the flowability of the concrete without recurring to the use of water. Silica fume makes the concrete sticky and cohesive. Therefore, a higher slump is needed to place silica fume concrete. It is normal to use 200 mm slump or 250 mm slump in silica fume concrete. Also, we should understand that silica fume concretes are prone to slump loss. So, we have to be careful in terms of the super plasticizer dosage and the time needed for transportation of such concretes. Bleeding is also reduced drastically. Bleeding is the excess water that floats to the surface and can be under the aggregates and rebars as compaction occurs. We will discuss it a little bit more in detail in the subsequent lecture. However, this bleeding helps when there is very high evaporation when the concrete is still fresh. If this bleeding is not there, then plastic shrinkage cracking can occur. That means water curing must be performed as soon as possible and as long as possible. So, bleeding is not something that we would like to encourage, but understanding that silica fume concrete is going to have less bleeding, we should start water curing as early as possible, prevent evaporation so that plastic shrinkage cracking does not occur. Within the concrete, due to the fineness of silica fume, we find that the porosity which normally occurs between aggregates and the hydrated cement paste is filled with this silica fume. There is this transition zone which normally occurs around the aggregates on the interface between the aggregates and the hydrated cement paste, which is generally porous. This is now filled with the silica fume and we do not get a weak or poor interface. Again, you see this here, that generally we would have a weak region along the interface, and with silica fume we fill up the interface and we have a more homogeneous and a stronger interface. So, this is what you would have without silica fume. In normal concrete, we have a zone here between the aggregate. This is the aggregate and this is the hydrated cement paste, and we find that there is a region here which is the interfacial transition. This is the interfacial transition zone which can be porous, has more crystals of calcium hydroxide, and this is where a crack can propagate, or if water gets through the concrete can also pass through. So, it affects both the strength and durability. Also, we find that this is where bleed water could have accumulated, leading to this porous zone. When we have silica fume, a similar picture where again this is the aggregate, we find that there is no weak interface between the aggregate and the rest of the cement paste. So, we have filled up the interface and we have eliminated the weak interface through which a crack can propagate or water can pass through. Consequently, however, we have made the concrete more homogeneous, and now the crack does not pass through the aggregate, the crack does not pass through the interface between the aggregate and cement paste, but passes through the aggregate. So, when high strength concrete breaks, you will see that the aggregates are also broken and you have a plain smooth crack face. This makes the concrete more brittle, but it also makes it very strong. This is something that we have to keep in mind. The aggregates, when they break, they increase the brittleness of the concrete, and when the crack goes around the aggregates without the aggregates breaking, then the concrete is less brittle. So, higher strength concrete is generally more brittle, and the reason is this, that we have made the interface strong and therefore the aggregates break, the crack goes smoothly through the aggregates instead of going around the aggregates and being deviated by the aggregates. The strength increase has been quantified. It is very well known that as we add silica fume, the strength of the concrete will go up. This is a graph showing the evolution of concrete strength without any silica fume. This is 0%. So, you find how the strength increases with time. This we discussed earlier. Same concrete with 5, 10, 15% of silica fume by weight of cement, we see how the strength increases. Beyond about 10%, there is not a major increase. This is the dosage that we generally use for silica fume, about 10%, because you see that between 10 and 15% there is not a major change. But from 0 and 10% we see a very significant change. 30 megapascal concrete can now be made into 55 megapascal concrete with this addition of 10% of silica fume by weight of cement. We also increase the durability. These are numbers showing the chloride permeability. Here chloride permeability is estimated by the rapid chloride permeability test of ASTM C 1202. This is a much criticized test, but it gives an indication of what happens to charges that are passing through. These charges are what could cause corrosion of the steel and other effects. We find that a concrete with no silica fume, 0% silica fume, say with a strength of about 35 megapascal, in this test could pass about 3000 coulombs of charge. Same concrete with 7 to 10% of silica fume, the charge part is reduced to less than 1000 coulombs, the strength also goes up 50 megapascal. With 10% of silica fume, the charge pass decreases to less than 500 coulombs, that is much less chlorides can get through to the steel when we have a high strength concrete of about 65 plus megapascal. So we find that the addition of silica fume increases the strength as well as the durability, because the impermeability increases. And if we look at the chloride content in a concrete that is exposed to chloride solution, this is a graph from Deere and Jones, where they show data of tests after 6 months of exposure to 1.9% chloride solution, different concretes. This is the concrete with only a Portland cement binder. This is the chloride content as a function of the distance from the surface. At the surface, all concretes have the same concentration of chlorides, but as we go in, say about 20 millimeters within the surface, a concrete without silica fume has about 1.5% chloride content, whereas something with 10-15% silica fume has much less chloride content. So that means the chlorides take much longer, they cannot penetrate very deep into the concrete and get to the steel. The other mineral admixture that we use very often is fly ash. Fly ash is obtained from the burning of coal in power plants. It is the ash that precipitates from the exhaust gases of coal fired power plants. These particles are spherical and have very high fineness. The particle sizes range between 1 and 100 microns. The Blaine specific surface ranges between 250 to 600 meter square per kilogram, little bit finer than cement. We have two types of fly ash, both are obtained in India. Common fly ash is class F, which is obtained from bituminous coal. From lignite burning we get class C fly ash, which is higher in lime content. So class F fly ash is pozzolanic. It has a combined silica, alumina, ferric oxide content of at least 70%, SO3 content maximum of about 5%, and a maximum loss of ignition about 6%. There is a lot of variability in this class F fly ash. The fineness, carbon content and color varies from plant to plant. In the case of class C fly ash, there is a high lime content as high as 24%, so it has some cementitious properties like slag. The carbon content is low and generally the fineness is high and the color is light. Nearly 75% of India's electricity comes through coal burning. So that means we produce a lot of fly ash. About 130 million tons of coal ash are being generated as waste product. About 50 to 60% of this ash is used by the cement industry, but lot of it still gets dumped. So more fly ash we use, it is better for the environment because we are using a waste product and not just dumping this fly ash in open land. Fly ash helps in the fresh and in the solid concrete or the hardened concrete. In the fresh concrete, because of the spherical shape, we have something called a ball bearing effect, where the flow is increased, the workability is better, and therefore the cement paste content decreases. Also we have less bleeding and segregation when we have a properly designed fly ash concrete. Again, because there is less bleeding, we have to take care of the curing, but we get a more consistent, more workable concrete in the case of fly ash concrete. The setting time is also increased. We can use the concrete for a longer time before placing. Finally, what is the influence of the fly ash on hardened concrete? The strength gain is slower the strength gain is slower. So, the concrete can take more time to reach its strength. On the other hand, you can think of it as a buffer strength which is there in the concrete even after 28 days. There is this additional concrete grain, there is an additional concrete strength gain even after 28 days. Creep and shrinkage are typically lower than in normal concrete because we have lower cement paste, and also we find that because of this lower cement paste, less cement content, we have better resistance against corrosion, alkali aggregate reactions and sulfate attack. So, we get much better durability also. So, we will continue in the next lecture with chemical admixtures, and we will also start looking at the properties of concrete which are important. Thank you very much. This took much longer, no?